I want to move into the, I'll return back to this in a second, well, in a few minutes. I want to go to the Polish notation. The Polish notation system. There's very little. First of all, I don't really know many, formal, proper logicians that use the Polish notation system. It's sort of like, okay, yeah, there's this cool other alternative method of symbolizing your arguments. Not only symbolizing your arguments, symbolizing, and it usually stops there. I don't think I've ever seen anyone, and I've read a lot of logic books. It's not to say that I'm the first person to do this, but I haven't personally seen any logic books where they use the Polish notation system to prove the validity of arguments within predicate logic. I've never seen that. It might exist, but I've never seen it. What I want to show you, and the whole point of learning this is, well, why aren't we looking more in detail at the Polish notation system? Because it's a more efficient system. The system's more efficient, right? It's there are less operators, not even less operators, there are virtually no operators. And insofar as the operators are lost, the system becomes more efficient, right? It takes a bit of practice to be able to understand what you're looking at, and I'm going to show you examples, and hopefully you'll be somewhat proficient by the end of this particular series right now. But no one's really doing it. So, hey, as a philosopher, I'm charged with the responsibility of bringing information to light. So I'm going to show you how the Polish notation system works. I'm going to do it very, very, very simply. Okay. First, let's talk about the system itself. There's an acronym that you can memorize. This is how I did it, right? Memorize this acronym. You memorize this acronym, you're 85%, and it's super easy. This is like 3rd grade level, right? Memorize this acronym, and you're about 85% through the way of understanding the Polish notation system, right? So it's Kaken, C-A-K-E-N, Kaken, right? C-A-K-E, like cake, N, Kaken, C-A-K-E-N. C is your conditional, right? Anytime you see a conditional, you're going to replace that conditional with the letter C. A is your disjunct. K is your conjunct. E is your biconditional. N is your negation. C-A-K-E-N. Okay, so that's the Polish notation system, right? Very simple. We see a conditional, however you write your conditionals. We see a conditional, we write C for the conditional. We see a disjunct, we write A. We see a conjunct, we write K. We see biconditionals, we write E. We see negation, we write N. So now that you see this, there really is no need for operators within your Polish notation system, right? You can get totally rid of it. How would we convert? Now the next question becomes, how do we convert our propositions into the Polish notation system? Well, this is how it goes. Imagine that we have if P, then Q. How would I translate if P, then Q into the Polish notation system? Well, what you do is, and I was thinking about the easiest way to teach this. Think about well, first we know that this conditional stands for C. What we want to do is we want to take all of our connectors, right, all of our operators, we want to take it out to the right of the, out to the left rather, of the letters, out of each particular statement letter. So this is going to go here, right? So that's step 1. We're going to move this operator out, right? So in a sense, it's going to look like this. In a sense, it's going to look like that, right? So that's, this is very, very introductory, and I want to make it clear. So the first thing that we do is we move it out to the left of the furthest left statement letter. So it looks like that. Now we replace, and then, step 3, we're basically done. Now we replace this operator with its corresponding letter. So it'd be C, you wouldn't write it caps, you write it uppercase, you write it lowercase. So it'd be C, P, Q, and that's how we write if P then Q in the Polish notation system, right? CPQ. what it's telling me is that between the P and the Q, there is the conditional, right? The conditional is connecting the P and the Q. So I would look at this and I would know, okay, that means if P then Q, right? So that's that. It doesn't seem so far that there's anything amazing about that. We'll see in a minute the benefit that this has. Imagine that we were looking at let's say P and Q, right? So P and Q, step 1, bring the conjunct out. Step 2, sort of rewrite it. P, it would be conjunct P and Q. Replace the conjunct with its appropriate letter. 3 would be K, and it would be KPQ. Right? So I would know that this means P and Q, right? And this is the way to do that. The thing that we can do now, right, is we can return to our discussion of NAND NOR operators and see that there is a relationship between NAND NOR operators, symbolic and predicate logic, and also this Polish notation system. We're all, in a sense, saying exactly the same thing. It's just a different way that we're saying it. And the point of this video, the first point of this video, is to clarify all the confusion. Right? So, let me show you an example. If we have, where's my example? Okay, imagine that we have if P, then Q. Right? We know that we can talk about if P, then Q as CPQ in the Polish notation system. But also what we recognize is that we can change this into our NAND NOR operators, right? In our NAND NOR operators, it's going to be equivalent to the claim P, Q, right? It's going to be, so all of these are the same, right? All of these are the same. They're completely interchangeable. I can use this to represent this. I can use this to represent this. I can use this to represent this. This to represent that. It's all the same. Okay, so that's the first part. Next, let's look at, I think conjunction is next. Next, let's look at the conjunction. P, what am I talking about? P and Q, right? And we talked about how P and Q looks, right? P and Q for this system is going to be, well, I erased it, but it's going to be KPQ, right? We know K stands for our conjunct, P and Q are letters, and its relationship is P, I think it's PQ, PQ. Yeah, PQ, PQ. So it's all the same, right? All of these are interchangeable, right? And this is a demonstration, and I can complicate it more, but I don't want to get any more complicated than this. This is just to show you that we're all saying the same thing, right? You can talk about NAND expressing if P then Q in this sense. You can talk about NAND as expressing the Polish notation system. You can talk about sort of regular symbolic as represent, and so on and so on and so on. There's an interchangeability between the various systems. All of these systems mean the same thing. Now, once we recognize that, right? Now it's going to get a little more advanced, right? Once we recognize that these are interchangeable, they're not like 3 distinct units of logic that don't have any connection, that we are all talking exactly the same language. Now the question becomes, why is our logic still so inefficient? Now I hope I don't get any complaints from people who are wedded to the old system. But why is our predicate logic as convoluted and inefficient as it is? And I think it is. Why is our symbolic logic as convoluted and inefficient as it is? If the point is, and the point should be, that we are continually attempting to increase the efficiency with which we deduce our problems, prove our validities, articulate our arguments, defend our points, critique and so on, the system should be efficient. The more efficient the system is, the more complicated we can get, the more intricate we can get. So this is nothing more than an appeal to increase intricacy within both symbolic and predicate logic by sort of borrowing, not borrowing, but just, you know, straight up using, in the black community, straight up bootlegging, some of these other forms of logic. So what you should know up until this point, it's important to know the true function for NAND NOR operators. Remember, the NAND, it's only going to be false when both are true. The NOR, it's only going to be true when both are false, just the opposite. We should commit this to memory, Kaken, right? This is going to be important, and I'll leave this up, for our substitution instances within our logic. And then a recognition, just a recognition, you know, just to show you that what we're saying is exactly the same. There is no difference. It's completely compatible, equivalencies across the board. So since we know that now we can get a little interesting, right? Now we can really get into an interesting discussion. Did I cover everything? Yeah. All right. So what I want to do is two things. One, I want to do first, if I have space, yeah, I want to do formal proof for validity in just symbolic logic. Then I want to do, of the video series that I did before, I don't remember which one it was. It was like 4 through 8. Two of those, I forget which two it was. I want to revisit the solutions that I gave in predicate logic, but construct the solutions in a different manner now. Now I want to construct the solutions in a more, what I would call, efficient manner, using the Polish notation system, right? And again, this is just an alternative method. It's not saying that the last method is worse and this method is better, or this method is worse and the last method is better. That's not what I'm saying at all. That's not the point of the lecture. The point of the lecture is to show you that we are all saying exactly the same thing. Which system seems to be the most efficient system, and that might be debatable. And then we can, you know, it's just an alternative method of solving problems. Similarly, like I did a video on my cube. I don't have my, well, this one, yeah, I don't have it, oh, it's across the table. But I did a video on alternative methods to solve the Rubik's Cube, right? You have your traditional way of solving the Rubik's Cube. I recognize that the algorithms that govern the Rubik's Cube do not apply to the colors, only to the placement, so that you can effectively inverse solve your Rubik's Cube. And I looked around the internet for months to see if anyone had done it, and I hadn't seen anyone that did do it. And it's just a cool new way to solve your Rubik's Cube, because the algorithms don't apply to the colors, they apply to the position. It's sort of like the same thing, right? The idea is sort of the same. It's like, well, we recognize that the solutions that we're doing are not governed by the symbolization itself, right? It's the logic at its deepest root. It has nothing to do with sort of whether I use this symbol or I use this symbol, right? We can get to the, and my ink is running out. It really has to do with sort of just the pure logic, and that's what I'm interested in, is getting rid of all the words, getting rid of all the ideas, and just looking at just the raw, pure logic. And as far as what I know until now, and if you guys know systems that are even more efficient, and quick point, we'll see why this is the most efficient. Look how long this is, right? In NAND, using NAND operators, right? Look how long, and the NOR operators is even longer than that. I forgot to put that out there, but look how long this is with NAND operators. Look how small this is. This seems like it's synonymous with this, but when it gets bigger, you'll see that even this so far seems to be the most efficient as far as the use of terms and symbols. So let's just for fun, see, and also to answer some of the questions that I have, see how advanced we can take both our symbolic and our predicate logic, right? Because all of this, again, as demonstrated here, it's all connected.